The first question that we have to address is, what is energy? How do we define energy? While you may have heard of nuclear energy, electric energy, solar energy, and so on, there is only one type of energy in the astrophysics universe, and that is kinetic energy. All these other forms of energy are just different ways to get molecules moving. Just like Maxwell brought together electricity and magnetism, Einstein's formula brings together energy and mass. These two were previously considered to be separate items. In this video, we'll see how energy is actually mass. In fact, Einstein in his original paper described mass as a function of energy over the speed of light squared. Let's illustrate how this formula works. Let's say for instance that we have 100 kilograms mass at rest, and that we apply a force to it until it reaches a velocity of 1/10 the speed of light. Einstein tells us that the change in velocity will result in a change in inertial mass. We'll do the calculations here to see how that works. The mass increase is given by the Lorentz factor. We multiply the rest mass by gamma to determine the moving inertial mass. We'll call it m prime. The Lorentz factor is 1 over the square root of 1 minus b squared, divided by c squared. We'll rewrite it like this, and, given that b is much less than c, we'll use the binomial expansion method to get the result. The binomial expansion method tells us that we write the first term, 1. The exponent, minus 1/2, multiplied by the second term to the power of 1. The following terms in the expansion will see increasing exponents, which, in the case of small v relative to the speed of light, get rapidly small. In this case, we get a good approximation with only the first two terms of the expansion. We can now get the value of m prime by multiplying the rest mass by the Lorentz factor. Solving for v equals 1/10 the speed of light tells us that gamma is approximately 1.005. The value of m prime is 100.5 kilograms. Now let's try to determine the amount of energy used to get the mass to this speed. From Newton we know that force equals mass times acceleration. Energy is equal to force times distance. In other words, energy is mass times acceleration times distance. Distance is equal to initial distance, plus initial velocity multiplied by time, plus 1/2 acceleration multiplied by time squared. We'll assume that the initial distance and initial velocity are 0. Velocity is equal to acceleration multiplied by time. We can express time as velocity over acceleration. Now we can calculate energy as the product of mass times acceleration times distance. Distance is 1/2 acceleration multiplied by time squared. We substitute time by velocity over acceleration and we have this expression. The a's cancel out, and we replace v by 0.1 c. Solving for energy, we get that this is 1/2 kilogram multiplied by c squared. This is the amount of kinetic energy that was added to the 100 kilograms mass to get it to a velocity 1/10 the speed of light. Einstein's formula tells us that energy has mass. When we increase the kinetic energy of the 100 kilogram mass, the mass of this energy is added to the rest mass to get the total inertial mass. This is the reason for the mass increase over rest mass. We made a small mistake by holding the 100 kilogram mass constant in this multiplication. The mass will start increasing as soon as it starts moving. But the error in this case is less than 1%, and it equals all the discarded terms in the binomial expansion. The correct way to do it would be using calculus, but this approximation is good enough for illustration purposes. For the rest of this video, we will call the increase over the rest mass kinetic mass, to indicate mass gain due to the velocity of the rest mass. It is important to note that kinetic mass has the same properties as rest mass, such as weight, inertia, and gravitational field, except that, as we are going to see shortly, kinetic mass can be transferred to other objects by the collision with rest mass. Now let's look at how we get energy. Let's consider, for instance, what happens when we combine hydrogen molecules with oxygen molecules. From chemistry, we know that this will produce water, but this is not all. When we combine 2 moles of hydrogen with a mole of oxygen, we get a mole of water plus 280,000 joules of energy. But what is the form of this energy? What is it? The real process is that this energy release is the result of that the rest mass of water is less than the rest mass of the hydrogen and oxygen that we started with, about 3 nanograms less. The energy content of the water is expressed as the molecular velocity gained by the water molecules. We call this heat. That is why we produce water vapor, not liquid water. The total mass is still the same that we started with, but the difference from rest mass has become kinetic mass. The hydrogen and oxygen molecules have lost 3 nanograms of rest mass, but the water molecules gain 3 nanograms of kinetic mass. Some molecules release some of their kinetic energy as photons. This is why we also see light. But most of the energy is in the speeding molecules. If we perform this chemical reaction in a closed vessel where no energy goes in or out, we could use a very high-resolution scale to measure the mass before and after the reaction. We would find that the weight is still the same, and the gravitational strength of the mass is also the same, but the inside temperature would be much higher than before. Another example of kinetic mass transfer is Newton's cradle. In this case, the momentum from the moving ball at one end is transferred to the other end when the collision occurs. What conclusion can we get out of this? It means that acceleration is a gain or loss of kinetic mass. Acceleration is absolute, relative to space. Acceleration is not relative. It also means that the total mass of the universe remains constant. Even after the trillions of stars in the universe burn hydrogen into heavier elements with lower rest mass, these heavier elements gain kinetic mass. Their total mass, rest mass plus kinetic mass, is equal to the rest mass of the initial hydrogen. But the ratio of kinetic mass over rest mass is constantly increasing. While there are some processes that transform kinetic mass into rest mass, such as photosynthesis, the overall tendency of the universe is to transform rest mass into kinetic mass. It is theoretically possible to convert all rest mass into kinetic mass. Some quasars, for example, convert up to 1/2 of the mass falling into photons, giving them extremely high luminosity. These quasars emit more light than the entire Milky Way. But for us here on Earth, there is no practical way to do that on a scale that would solve our energy problems. Photons are particles that have no rest mass, only kinetic mass. This is why they can travel at the speed of light. Because photons only have kinetic mass, collisions between photons are not possible. The momentum of a photon is given by this formula, Planck's constant divided by its wavelength. The units of Planck's constant are kilograms times meters squared, divided by seconds. The units for lambda are meters. Meters cancel out. Meters per second is velocity, which in this case is the speed of light, and we have kilograms times c. Since the momentum is not zero, this kilogram quantity cannot be zero. Scientists have been trying to move away from the concept of relativistic mass, and for good reasons. There are still big questions regarding kinetic mass. We know that a proton at high velocity does not increase in size. The amount of charge also remains the same, but it behaves as a more massive particle. How does kinetic mass get transferred from one object to another? There are still mysteries about kinetic mass. Einstein did not like the idea of variable mass. The preferred terminology now is to refer to particles by their energy or momentum. The concept of energy is more familiar, but this is trying to hide the problem in plain sight. For one, energy does not distinguish between rest mass and kinetic mass. Rest mass is constant, while kinetic mass is variable. Kinetic mass is a different state of matter, and it has some properties similar to dark matter. The second problem is that Einstein formula tells us that energy is mass, and mass is energy. We have seen how E equals mc squared works. This is a well-known formula. But also, inertial mass equals rest mass times gamma is an equally important formula for quantifying the amount of kinetic energy. These formulas can be combined into one by describing energy as equals to total inertial mass times gamma minus 1. This is the formula that Einstein wrote in his original paper, and it is what we derived in these calculations. We can thank Einstein's genius for developing these formulas and allowing us to better understand the workings of our universe.